All right, so moving into chapter 10, we're going to be talking about what's called potential energy, and also get to the equation describing conservation of energy. Now, potential energy, one way to think about it is some sort of stored energy. Ultimately, it's the energy that exists because of an interaction between some sort of object, a box, a crate, and the earth or a spring. So at the end of the last chapter, we said that the work done by gravity essentially can always be written as minus mgy final plus mgy initial. The amount of work done by gravity depended on the mass of the object, the acceleration due to gravity, which of course we're considering constant, and then simply the initial and final vertical height, the vertical position. It only related to the height the object moves through. Because of that, we define gravitational potential energy as mgy. We use a capital U to represent gravitational potential energy, so subscriptive G to represent specifically gravitational potential energy. If we account for potential energy initially and finally, then we can account for what gravity, the force of gravity, is going to do, whether it's going to do work or not, on the object as it moves in any given problem. So, work done by gravity, if I am calling mgy this gravitational potential energy, then this is negative U final for gravity plus U initial for gravity. It's a negative delta U for gravity. Well, similarly, a spring, the work done by a spring only depended on the initial and final compression or stretching. It doesn't depend upon how it gets between those two, the initial and final, just what the initial and final are, similar to gravity. So we define elastic or spring potential energy, stored energy, simply because we have an object that is either compressing or stretching a spring. This potential energy accounts for what the spring can do. Now, in the test notes, I believe they have it written as 1/2 K delta S squared, because that is the notation our author chooses to use. Again, I like to use S just to minimize my variables, but I do need to remember that S must be measured from equilibrium. That's important. All right, so gravity and the spring are the two specific conservative forces that we have talked about. Now, friction is not conservative. Work done by friction does depend upon path. Work done by the kinetic friction is always negative. It's taking energy out. Because an object sliding on another surface causes the temperature to increase, we say that thermal energy is generated. we can say the energy generated is equal to the opposite of the work done by friction. So it's going to be the force of kinetic friction times the distance the object slides along the surface. All right, so pulling these all together, I can say, come back to spring, I forgot to mention, this can be written as negative delta U for a spring. We also call this elastic potential energy, just, you will probably see that term. So you want to be familiar with it. All right. So what we're going to do, so far to relate forces to motion, we've been using, in terms of this section, I should say, we've been using the fact that the net work done on an object is equal to the change in kinetic energy. Now, by net work, we mean the work done by every single possible force. So, work done by gravity, work done by a normal force, if there is a normal force, work done by friction, work done by a spring, work done by any other type of force we can think of. So the sky's the limit. All sorts of forces are acting on objects, not all at once, but this work done by like a tension, if there's a string. So this is our work done by any other type of force. Other than gravity, normal, friction, spring. So generically, if we find the work done by any possible value and force, it will equal the change in kinetic energy of the object. But, as we've just mentioned before, we're going to define this stored energy because of what the Earth can do for this object or on this object to change its energy. In place of work done by gravity, I'm going to put negative delta U for gravity. Work done by a normal force is always going to be zero because the normal force is always perpendicular to the surface that the object is sliding on. Work done by friction, so coming up here, work done by friction is going to be negative delta E thermal. The work done by friction is creating thermal energy, but the negative sign just means it's coming out of the system, essentially. Work done by a spring. Well, we can talk about a spring in terms of potential energy as well. So negative work done by a spring. That covers all of those. This work done by any other force, we're going to call this work external. So work done by any other type of force, we're just calling these some other type of external force. It could be a tension, it could be some sort of push or pull, but we cannot account for those in terms of thermal energy or potential energy. So we're just calling it work external. So this has to equal our change in kinetic energy, which this, as it's written right now, doesn't look terribly exciting. If I bring the delta U's to the other side and the delta E thermal, I don't know if you happen to remember. Actually, let me go grab it. Hold on. Okay, at the beginning of covering this section, did that not copy? Okay, so I found the figure. Beginning of this section, I pulled out this figure from our book. It's telling us that within a system, energy can be transformed between kinetic, thermal, potential. Chemical's not one we're going to specifically talk about, but that is within a system. If we add energy from their environment by way of work, we can increase the energy of this system. Or if negative work is done, we can remove energy from the system. This equation is essentially describing that portion. Any work done by forces external to the system, so not gravity, not a spring, not friction, any additional work will change one of these at least, if not multiple. It'll change the kinetic energy or the potential energy. So we will get a total change in energy of the system as a whole. If there's no external work done, then any transfer of energy happens within the system itself. And we can describe that in terms of this kinetic energy, potential energy, thermal energy. And these are describing the energy transformations within the system. Now, we're not going to talk heat yet. When we talk about sliding a box across a table, across the floor, heat is not really significant. It's not at play. Heat is the change in, is causing a change in energy of the system because the system itself is at different temperatures than its surroundings. Everything we're looking at happens too quickly for heat to be important. And so we are leaving that out until chapter 19. So ultimately, what I want to do is I want to show you what the conservation of energy equation looks like. We tend to combine these two potential energies together and just call it delta U. In solving problems, we need to remember there's two types of potential energy. But just to simplify the equation down a little bit. All right, so where we're going to go with this, with our conservation of energy, the way you will see this equation is we tend to bring the initial values to one side and final values to the other. So remember, delta K means K final minus K initial. Delta U means U final minus U initial. Delta E thermal, we just leave it as delta E thermal. We could call it just E thermal. Essentially, we're just saying some thermal energy is created or generated because of kinetic friction. If I bring the initial values over, my equation looks like this. The order of adding doesn't matter. I wasn't consistent. I guess that's going to kind of bug me, so let me do that. U final plus K final. This is our equation that represents conservation of energy. Energy conservation means energy is always there. So we don't create new energy, we don't lose energy, it is always in existence. It is just changing from one form to another. So when we talk about potential energy and kinetic energy together, we refer to this as mechanical energy. This is energy in terms of motion, energy that can easily transform back and forth. Potential to kinetic, kinetic back to potential. So mechanical energy initially on the left, and mechanical energy finally can only change if thermal energy is generated. So thermal energy is generated if there's kinetic friction. Kinetic friction, so a box sliding on the floor, the temperature increases. That is a specific change in energy. Work external is any other energy added or removed because of other forces. Because of the external forces I mentioned above. External. By that, I mean not gravity, because we're accounting for gravity and the spring in terms of potential energy. So this external forces is not the force of gravity, not the force of a spring, not the force of kinetic friction. Because we are already accounting for those in terms of potential energy or thermal energy. So there has to be some other force, some sort of push or pull or tension that would be causing the energy to change. This is a beautiful relationship though. Vectors are not here, so we either have gravitational potential energy or we do not. Now that is assuming mgy, because g is constant. When we get to chapter, I think it's 13, we start talking about like the energy the Earth has because of its orbit around the sun. Lowercase g is not a constant anymore in that case. So this equation mgy specifically applies as long as g is a constant for the whole problem, which is going to totally be the case for all of our problems right now. Our elastic potential energy or spring energy is 1/2 ks squared, where s is how far the spring is stretched or compressed from equilibrium. Kinetic energy, energy of motion, anything moving has kinetic energy, and then thermal energy. This is the positive. Kinetic friction force times delta S. And yes, you can totally do friction times distance. I keep trying to not do it because I'm trying to be consistent with our author. This equation is fundamentally the same as the net work equaling kinetic energy. So it's just another way of looking at it and looking at different types of energy as opposed to just kinetic energy. This is the equation we will use throughout chapter 10 to calculate or to relate forces, heights, distances together. This is the approach I prefer, and so that's why I kind of rushed to this section. It turns out most of the problems in chapter 9 you can technically solve using conservation of energy. So if you would like to do that, that's totally fine. When it comes to your tests, I don't care if you use net work equals change in kinetic energy or conservation of energy. It just needs to be concepts from this section specifically.